This is the formula for the position of a simple harmonic oscillator. And you can see we're expressing the position in terms of the cosine function. And it's a function of time. You can see time is here inside the argument of the cosine. And, x is position, t is time, of course. A is amplitude. Omega is the angular frequency. Again, t is time. And this is phi. This is called the phase shift. And I want to go through and explain what the phase shift is and why it's important. So, to begin with, we're going to start by looking at t equals 0. So we're going to look at the initial position and what this function gives us. So if I go to t equals 0, what I get is a times the cosine. Now if t is 0, this isn't going to matter anymore. And so we just have the phase shift. And so you can see from this that the phase shift directly correlates to the initial position. Now the phase shift has to be measured radians, and it can be anywhere between 0 and 2 pi. Typically though, there are 4 important phase shifts. And those are, if we let the phase shift, so if the phase shift equals 0, then the initial position, x0, which I'm just going to say x initial, that's the initial position. Cosine of 0 is 1, so it just becomes the amplitude. If the phase shift is pi over 2, because remember it has to be in radians, so I wouldn't say 90 degrees, I'd say pi over 2. Then the initial position equals the cosine of pi over 2, or in other words 90 degrees, is 0, so that's 0. If the phase shift is pi, then the initial position, the cosine of pi is -1, so the initial position is -a. And if the phase shift is 3 pi over 2, then the initial position is 0. Cosine of 3 pi over 2 is 0. I could do 2 pi, but 2 pi just starts the cycle over again, right? So then I'd just be back to here. So these are the 4 significant phase shifts. These are also the common ones. Again, it could be anywhere between 0 and 2 pi, but these are ones that you typically see. And the idea here is if the simple harmonic oscillator starts at the positive amplitude, that tells me the phase shift is 0. If it starts at 0, I don't know, that could be either one of these. We'll come back to that. It could be pi over 2 or 3 pi over 2. But if it starts at the negative amplitude, then I know the phase shift is pi. Okay. And the phase shift is important because it's allowing me inside the argument of the cosine to essentially say where this object is starting, where it is at the beginning. That's what the phase shift is telling me. Now the phase shift itself doesn't actually tell me where it starts. I mean, this is where it actually starts, these values here. But it does correlate it in terms of the argument of the cosine. And so if you want this function to accurately tell you where the object is, you have to include the phase shift. Now I want to take a closer look at these two cases right here, pi over 2 and 3 pi over 2. So if I'm looking just at those, now let me just say, if an object starts at 0, you don't know if its phase shift is pi over 2 or 3 pi over 2 unless you have a little bit more information. And that extra information you need comes from the velocity function, because the velocity function actually looks very similar. The velocity function is negative Vmax sine of omega t plus the phase shift. And so we could do a similar thing. We could say, okay, what happens to the velocity function at the beginning? What is it at t equals 0? And this becomes 0 again, and you get negative Vmax sine of the phase shift. And so you can go through and ask yourself again, okay, if so let's go back to the beginning. So if I say, okay, the phase shift is 0, well now, then what I get is that, now we already knew what we got for x. We said x equals a, and v, this is x initial, excuse me, this is v initial. X is a, v initial, so I put in the phase shift to 0. The sine of 0 is 0. Okay, so this makes a lot of sense. My object starts at the amplitude and it has no initial velocity. Well, yes, because we know that when it gets to the amplitude, we can just reason through it. That's the moment it stopped. If it was still moving, that wouldn't be the amplitude because it would still be going. So then the next one is phi 0 equals pi over 2. Okay. X initial, we've already identified this, is 0. And v initial, okay, so pi over 2, the sine of pi over 2 is 1. So this becomes negative Vmax. Okay. Now let's do, I'm going to skip pi because I want to focus on the two oddballs here, the pi over 2 and 3 pi over 2. At 3 pi over 2, the sine of 3 pi over 2 is 0. But the sine of 3 pi over 2, I'm sorry, I said that wrong. The cosine of 3 pi over 2 is 0. The sine of 3 pi over 2 is negative 1. So this becomes Vmax. This x equals 0, that's the equilibrium position. And that's when it's moving the fastest. And the difference between these two phase shifts here is the direction that it's moving. With 3 pi over 2, it's moving in the positive direction. With pi over 2, it's moving in the negative direction. So you have to take a close look to figure out which way is it moving. Now I did skip, by the way, the pi. For pi, the only difference is if it's pi, your initial, as we already discussed, the initial position is negative amplitude, but the initial velocity is still 0. But for the pi over 2 and 3 pi over 2, the initial position is 0 for both of them, but the initial velocity is different. Again, for the pi over 2, it's moving, it's at the equilibrium position, but it's moving in the negative direction. For the phase shift to 3 pi over 2, it's at equilibrium, but it's moving in the positive direction. So that's the difference between these two. And the last thing I want to take a look at is how to tell by looking at a graph. What are you looking for? Okay. So if I'm looking at a graph, so I'm just going to make a graph here. And I'm going to draw one like this. And this is going to be my position graph. So this will be x, I'm messing this up. I'm sorry. This is t. This is time. And this is the x position. This is x of t up here for the vertical axis. And you can look right here. This is where, so this is the beginning. This is t equals 0. So this is the initial position. So I can see from this graph right there at this point, oh, it's 0. X initial is 0 right there. Right. Now, again, that doesn't tell me the phase shift. The phase shift could be pi over 2 or 3 pi over 2. So how do I determine which case it is? Well, now I take a look at the slope. Remember, the slope of a position graph tells us the velocity. Okay. The slope of this, now I don't know what the slope is, but I can look at it and see that the slope is positive. because the slope is positive, that means the velocity is positive at the beginning. So this started at the equilibrium, and it had a positive velocity at the beginning. So that tells me that V initial is greater than 0. Therefore, I know in this case, my phase shift is 3 pi over 2. Now, if you've ever dealt with trig functions, there are other ways to go about looking at phase shifts in terms of seeing how the graphs work. You're welcome to look that up on your own. I wanted to make sure everybody's clear in terms of the physical nature of this, what this is representing, how we're able to figure it out. That's my goal here. And so you need to understand what these phase shifts correspond to in terms of the initial position and the initial velocity, and how to use that knowledge to either figure out the phase shift, or if you know the phase shift, then that's telling you something about the initial velocity and the initial position.